So here's number 19 from section 7.3. Let's do some drawing and see what this you know what? You got a problem. I don't know what I'm rotating this thing about. It's always their x-axis? So this is about the x-axis? Okay. So let's start by drawing out our curves. Here's the y equals secant curve. Comes down to there and touches at 1. Y is equal to square root of 2 is like this. And now we're going to rotate this about the y-axis, which means my reflection is down here at -1. This point revolves around to that point. This point revolves around to that point. This point revolves around to that point. What does this look like to me? It looks like, on the outside, it looks like a cylinder. But in the inside, instead of being leveled off on both sides, it's like stuff has been taken out of it. And it's like empty inside, like a... It's like a donut, but you cut out the outside edge. Okay? Yeah, that's really... So if you thought of a donut... Donut's like if you revolve the circle around, and what you've done, we've chopped off this outside part, so now it's like a cylinder on the outside, and it's like a donut on the inside.
So no, it's like an empty cylinder, or is it like, is there stuff in it, but there's like a circle of it?
But there's a hollow, where my hand is right now, it's all hollow.
Are you inside the cylinder?
What?
Are we thinking like a can?
Okay, wait. In this orientation, there's my cylinder. That's what it looks like on the outside. In the inside, though, think of this as like an empty tin can. In the inside, the sides aren't flat on the inside, but rather it's got stuff that's stuck to the inside of the can.
So it's basically...
But it's still got a place where I can put my hand in. It's still hollow inside, but the edges kind of bulge in.
It's just the opposite. Yeah.
All right, let's go on. Now, let's try doing this using a washer method. I'm going to draw using that circle and this circle, a typical washer. That washer is in an orientation in which the thickness is dx. So as I start attacking this volume problem, I'm looking for a formula that represents the cross-sectional area, and all my numbers I want to be numbers with, or expressions with x in it. All right, let's see. The washer has a big outside circle, and the big outside circle has a radius which goes from here all the way to there. That big outside circle has a radius of √2 squared, and so there's my big outside circle. The area is pi times √2 squared. My washer has an inside circle. It has a radius that goes from here up to the secant curve. So it's going to have a radius of secant x, and there's my expression for the inside circle that I'm subtracting out. And again, this is dx. Lastly, I need to know what range of values, oh, we're already given them right here, aren't we? We're saying the values of x range from negative pi over 4 to pi over 4. Negative pi over 4 to pi over 4. And now I get to cheat. You're okay with cheating, right? How am I going to cheat? Take out the pi. I can take out the pi. Excellent. And I get 2 minus secant squared x dx. There's one other thing I want to cheat, though. This volume is symmetric about the y-axis. There's just as much volume in the negative x area as there are in the positive. So what I'm going to do, instead of going from negative pi over 4 to pi over 4, I'm going to go from 0 to pi over 4, and I'm going to double the area, or double the volume. And now what do we got? Antiderivative time. Antiderivative of 2 is 2x. The antiderivative of negative secant squared is tangent x as evaluated from 0 to pi over 4. Two pi times 2 times pi over 4 minus tangent of pi over 4. Here's me evaluating it at the top end. Minus 2 times 0 minus tangent of 0. Times 0, tangent of 0. It's all 0. Ignore that part. And so what do we get when we distribute? 2 pi times 2 times pi over 4. Well, that 2 and that 4 become a 2. When I multiply that through, the 2's go away. I get pi squared. Tangent of pi over 4 is 1. So when I multiply, I'm going to get a 2 pi there. And that's what they say the answer is, too. And that's how we do those problems. I don't think this is where the problem is. I think the problem is writing it. Getting to the point where we got the integral written. You know, all I can tell you is that I have so little talent from the artistry side that I know that the things that I do is that I tend to, again, draw the reflection of the region that's getting twirled around the axis, and I try to draw circles that connect corresponding points. So can you visualize that hole on this side? Can you see the bulge there? And then, of course, all those circles. And you don't really draw circles, you're drawing ellipses because you're seeing them on like their edge.
And another thing is, what is the purpose of you twirling around? What does that apply to?
Well, a lot of manufacturing processes are done by twirling things around and then scraping things away. For example, if you think of a lathe, you know, you put a dowel between two, you spin it around, and then when you cut, things are equally cut around it. That is creating a volume of revolution. That's creating something that's what's left over is, you know, have all circular cross sections. Pistons in an engine have similar ideas. So these volumes of revolution do have their places in the manufacturing and the physical sciences. Okay, that was problem 19.